Hello, hello, hello. Welcome back. It is Tuesday, the 21st of April, and today we're going to be going through some nuclear physics. So I've definitely had a schedule reshuffle on this side of Easter. A bunch of people dropping out or moving to a different slot or moving to exam leave timetable. And then new people coming in on my Wednesday means that today, on Tuesdays moving forward, is when I'm very likely to be carrying on these physics seminars, going through different topics. So that's just something to look out for. I know you got a 2-in-1 today, so I imagine there are very, very few people who have watched both. Given that this morning I did a GCSE paper, the second GCSE paper from the 2024 series. Thought I'd pop out a couple of those just for my students doing GCSE math, just to make sure you get like the exam technique, things like that, how to check the work. But today is going to be all about nuclear physics. So if I have time, I'll go back and do the sort of radiation stuff, the alpha, beta, gamma stuff. But I think that is kind of stuff that you've covered more from GCSE. And so the stuff that's new to the A level is this nuclear energy stuff. It's the binding energy stuff. It's the binding energy curve. A lot of that stuff is very new, and it's stuff I have to go through a lot with students. So I think that is a good place to start. And I've got a hard stop at 7 because I have a session. So it may be that that's all I get through in order to do it well. But if I have time, I can go back and do some of the radiation stuff as well. And as always, feel free to drop stuff in the chat, in the comments, drop some questions. I'll be able to sort of cover those as required. So let's move you over there and let's get into the whiteboard action. So, in fact, let's talk about the theory of where this all comes from. So we'll start with you guys up here. Okay. So we know by this point that a nucleus is made up of protons and neutrons. And we know that there is a strong nuclear force holding them together because those positive neutrons would be electrostatically repelling. So there must be some force holding them together against that repulsion, and that is the strong nuclear force. So you have a bunch of nucleons held together with a force. So to split those nucleons apart, you have to do work against that strong nuclear force. And we know that work done is energy transferred. So what is that energy transferred into? You have at the start a nucleus composed of protons and neutrons. You do work to separate it. It was standing still. It has the same sort of GPE. The thermal energy can't increase because that is the kinetic energy of particles. You just take it as it is and you split it up, and you got a bunch of protons and neutrons just separate. That work done has to have been transferred into a form of energy. And that energy is mass energy. That is the point of E equals mc squared. You take that work done you put into it, gets stored as extra mass on the separated protons and neutrons. And so that fact that they have different masses, well, that difference is called the mass defect. And so by calculating the mass defect, the difference in the mass before and after you separate those nucleons, you can work out how much energy went into separating them. And that's defined as the binding energy. So the binding energy is the energy you have to put in to separate a nucleus into its constituent nucleons. So we can give an example. Now, I'll also say there's 2 routes for doing this, right? So you've got the route by which you use the E equals mc squared equation, where you take the mass defect in kilograms and use E equals mc squared to convert that into energy in joules. Or, as is more often the case, you calculate the mass defect in atomic mass units and then convert that into electron volts, knowing that 1 atomic mass unit is 931.5 mega electron volts. So let me go through an example or two of that, just to make sure you guys are really okay with your binding energy equations. And if you've encountered any really difficult binding energy questions in your sort of studying, feel free to drop those and I'll make sure to tackle those as well. But for more of a basic one, let's say we have a situation where polonium-210, nope, that is an eraser. So let's say we have polonium-210, 84, and let's say it's releasing an alpha particle. Or actually, let's just calculate the binding energy of polonium-210. Why not? So what that gets split up into, therefore, is 84 protons, and 210 minus 84 is 126 neutrons. That's what it would be if I separate it out. Now, we can work out that mass defect because, well, you have to be given it, but let's say, so the mass of the polonium-210 is given as 209.93667 lots of U. And if I get myself a formula book real quick, because these I most certainly do not have memorized. So AQA, A-level physics, formula book, formula sheet. If I look this up, I find that a value of the mass of the proton is so 210 polonium is that. Mass of a proton is given as 1.00728 U, and the mass of a neutron is 1.00867 U. First of all, let's talk about why this would be the case. Why is it, if U is atomic mass units, why would a proton and a neutron be heavier than 1 U? And that comes from the fact that U is defined as 1/12 the mass of the nucleus of carbon-12. So you would have to put energy into splitting up a carbon-12, and that is stored as extra mass in the protons and neutrons. So it makes sense that a proton and a neutron would be slightly more than 1 U. So here we do 84 times the 1.00728. And we add that on to the 126 neutrons at 1.00867 a pop. And when I run that in a calculator, I get 84.10728 plus 126 times 1.00867. And that gets me 211.70394 U's after separating. So we started off with 209.93667 as a nucleus. And when I separate it, I find that there is this extra mass. So the mass defect is given by that difference. So you always just work out the difference before and after. And in terms of U, that gives me 1.76727 lots of U. So that is the difference in the mass. And then understanding that one atomic mass unit is 931.5 mega electron volts. You can simply multiply that 1.76727 by the 931.5 and get the binding energy, 1646 mega electron volts. So that is the energy required to split apart the polonium-210 into its constituent protons and neutrons. And this works in any situation. In any situation, it's not just the separate protons and neutrons. So let's say instead we were doing a specific reaction, right? So let's say we were doing the 210 polonium instead undergoing alpha decay. And when it does alpha decay, it would turn into 206 lead. 82 and a 42 alpha. In this case, we still do the before and after, but in this case, we have to be given a little bit more about what these before and after masses are. So we'll use the same mass of the polonium-210 as being 209.93667 U. And if we have the 206 lead, has a mass of 205.92936 U, and a 42 alpha as being 4.0010 U, then by adding these two together, we get the total mass after 205.92936 plus 4.0015. So that would be 209.93086 U, which is much closer to this mass of the polonium-210, but is still different. So if we take that mass difference and do the 209.93667 minus this thing, you get 0.00581 U. And again, if I multiply by 931.5, I find that the energy released is 5.412 mega electron volts. Is binding energy a type of potential energy? I suppose in the sense that you could consider mass to be a form of potential energy, yes. But it is also very similar to gravitational potential energy, where it falls as you move in, and you can change the height, and exactly the same way that here that you can kind of change the map. Well, if potential energy is energy stored, then yes, let's call it that. And so when you're doing like a nuclear reaction, like in a nuclear reactor, you have these things happening. They're releasing, you're releasing energy because that's being released from the mass. So it's stored in the mass and then released, and you can get that back by reforming the nucleus. So I'd be happy calling it a potential energy. They never really ask you about that, but yeah, no, that is an interesting theory point. Definitely the case. And yeah, and thanks for asking that in the chat as well. So we've talked about the strong nuclear force. We've defined binding energy. We've defined mass defect. That's all fine. Because I think as well, let's talk about it in terms of this binding energy curve, because I think that's where things will start to make more sense in terms of the stability of nuclei. So what we can do is, by finding the mass of the nucleus, like we did here, as 209.93 this, we can work out, as we did here, the binding energy of every single nucleus. And then, in order to better compare different nuclei, we can standardize it by dividing by the number of nucleons, by dividing by that mass number. And that would give us the binding energy per nucleon in order to better have a like-for-like comparison between different nuclei. And when we do that, we get the classic curve, where if we plot binding energy per nucleon, and it's really important that it's per nucleon, if we plot that against the mass number, so binding energy per nucleon, well, I suppose I shouldn't use that because, as you know, the slash means something. So if we plot that in mega electron volts versus the atomic mass number, please could you recap half-life? Yes, I can. But for now, I'm going to go through the rough shape of this curve where it goes up and then it plateaus and goes down slowly. In fact, yes, I will definitely go through that. I may not go through like the basics of alpha, beta, gamma, but I will definitely do that because there's, in terms of the equations, I think there's really important things to know. So what we find is that the binding energy per nucleon, roughly speaking, increases up until you get to iron. Iron 56, I think. That is the most stable nucleus. And why do we say it is stable, right? Why does that indicate stability? Because we can almost think of these nuclei as having like, you can think of it if you do chemistry as being like a Hess cycle. So we know, for instance, if I have the pen like this and I let it fall, it has become more stable because its potential energy has decreased. Things tend towards sort of energy wells, right? And so by releasing energy, releasing GPE, you've made it more stable. You found a more stable equilibrium position for it. And similarly here, the binding energy per nucleon, you can think of every single nucleon, that if you think of the binding energy as the energy required to break apart the nucleons, the more energy you have to put into breaking them apart, the more stable they were. So per nucleon, the binding energy means the harder it is to separate them apart because they are the most stable. And so things can become more stable by increasing their binding energy per nucleon. And the way you do that here is by fusion on this side, by taking lighter nuclei and smashing them together to form heavier nuclei. And on this side, we have fission, where you become more stable by breaking up into smaller nuclei with an increase in binding energy total. Carbon dating felt a bit weird when my teacher explained it. Yeah, we can go through that. But first, I really want to explain how this works in terms of, so how would I work with a graph like this, right? So let's say I had something here. What I could do is this energy here. So I'm going to make up some random numbers now. This is not physically accurate, but I'm just sort of, let's do it. So let's say this is uranium-235. That is accurate, and that's the fuel for fission reactors. But now I'm going to say, let's split that up into something with a mass of 135 and something with a mass of 100. So what we could consider this to be is if I call this height, okay, so let's do this, right? So let's say if I call this value A, this value B, and this value C for these respective binding energies per nucleon. That means that the energy required to separate the uranium-235, this binding energy, would be equal to 235 C. And then how much energy would I get out when I recombine those nucleons into the new nuclei? Well, I would get 100 A released and 135 B released. And so the total energy released would be equal to that 100 A plus the 135 B minus the 235 C. Let me move that so it's less in the way. Whoop. So you can use this diagram to work out the total change in energy. And by the way, what I like to do conceptually for me is I can consider instead, hold on, if I drop that back down again, we can consider instead, let's say we start here and track across. Then what that means is 135 nuclei have had their binding energy increased by this amount here, and 100 nuclei have had their binding energy increased by this amount here. And so you can see that the binding energy is increased, so it becomes harder to separate them, and by that energy being released, the potential energy is dropped into a more stable state. So you can kind of think of it in two ways. Either in this Hess cycle form, where you release the energy to form all the nucleons and then recombine them to form new nuclei, or sort of track across and see that visually. This is binding energy. Binding energy for A-level and for IB. So this is how you can use the binding energy per nucleon to predict the stability and whether something will undergo fission or fusion. I think from here, do I want to do like the full? I'd rather stick to the core theory. So I think in terms of, like, maybe I'll come back to this and do fission and fusion reactors, but I think based on chat, I think we'd rather go through core theory of this binding energy stuff and then go back and do the core theory for like the radioactivity stuff. And with that, I think that is the core of binding energy, where you really just calculate the mass defect exactly and half-life. Okay, so we'll move on from this now. And I'll, based on popular demand, let's do some half-life stuff. So you know your alpha, beta, and gamma. Let's have this, okay, bring you over here for, let's have a little chat. So you know about radioactivity. You know alpha, you know beta, you know gamma. You know that alpha is a helium nucleus, 4 protons, 2 neutrons. It is the most ionizing, it is the least penetrating, and gamma, beta is a high-speed electron, and gamma is a high-energy photon. It is the most penetrating, it is the least ionizing. So we know all of this stuff. I don't think I really have to go through that too much. I think you also know the uses from GCSE. But what I really want to go through is this theory of radioactive decay. So the first thing you have to know is that radioactive decay is a random, spontaneous process, where both of those words are very significant physically. Random means you cannot predict when a nuclei will decay, and in a given second, you cannot predict which nuclei will decay. It's probabilistic. And spontaneous means it's only dependent on internal factors. Like there's nothing you can do externally to increase or decrease the rate of fission, of decay even, sorry. So for instance, in the way that like with chemistry, if you increase the temperature, you increase the rate of reaction. If you increase the temperature, you do nothing to the rate of decay. It does not depend on external factors, only internal factors. So it is a random, spontaneous process. Now that randomness means it is probabilistic. So in a given second, there is a certain probability of any nuclei decaying. And that is what the decay constant is. The decay constant is the probability of a nucleus decaying in a given second. Background radiation, oh yeah, we can cover that. That is the classic trap. So let's say we had N nuclei. Oop, I have to start sharing my board so you can actually see it. That's how that works. So let's say we had N atoms, right? The activity is the number of nuclei that decay in a given second. And so that is the number of nuclei N times lambda, the probability of a nucleus decaying in a second. So this gives the relationship between activity and N, the number of nuclei. And by the way, if you're wondering why it undergoes exponential decay, it is because of this exact equation. Because A is the activity, it's the number of things that decay in a second. So you could consider A to be the rate of change of N. So this is a bit of a tie-in for anyone doing further math or even single math. Or the exponential distribution and the half-life length. If I knew enough about the exponential distribution, I could answer that question. But I don't. So instead, what I will say is activity is the, if you can consider it to be the rate of change of the number of nuclei. So that you can set up a differential equation if that's something you're comfortable doing. And we can say that dn dt is equal to minus lambda n. And then this becomes a differential equation you can solve, right? So the integral of 1 over n dn is equal to the integral of minus lambda dt. And solving that differential equation, you get ln n is equal to minus lambda t plus c, which means that n is equal to e to the minus lambda t plus c, which is where we get n equals a e to the minus lambda t, and when t equals 0, we know that n is equal to n naught. And by substituting that boundary condition into this equation, we find that n naught is equal to a, which is where the equation comes from. N equals n naught e to the minus lambda t. So that's just a tie-in for anyone coming from the math syllabus. Okay, so the fact that the rate of change of the nuclei is proportional to the number of nuclei left means that you get this exponential decay, where this lambda is the probability of any individual nucleus decaying in a given second. So we've just derived down here that n is where n is equal to n naught, where n equals n naught e to the minus lambda t. But that therefore means that a is equal to lambda n naught e to the minus lambda t. So in other words, a is equal to a naught e to the minus lambda t. And so a experiences exactly the same exponential decay. And by the way, let's talk about the relationship between activity and count rate. So activity is the number of nuclei. The activity is the number of nuclei that decay. But just because a nucleus decays does not mean that the radioactivity it produces is picked up by a Geiger counter. That radiation gets radiated kind of in just possibly in all directions, as is the case with gamma. Obviously, depending on the source, you can get it to fire out in a specific direction. But just because it releases some radiation does not mean that radiation necessarily gets detected. So physically speaking, if we were like firing some radiation and we had our Geiger-Muller tube here, it wouldn't pick up on all of the radiation. It would only pick up on a proportion of the radiation. But it would still be dependent on the activity. So we would expect that the higher the activity, the higher the count rate would be. And so using a similar scale factor argument, you could say that the count rate from the source is also equal to initial count rate e to the minus lambda t. So in a graph, excellent question. So in a graph, what we'd expect, let's just start before we, and then I'm going to add the background radiation in next. But if we start first, we would have these. In fact, I should let's do them side by side. So 1, 2, 3. So we've got number against time. We'll have activity against time, and we'll have count rate against time. They will all have the same exponential decay curve, where this would be C naught, this would be A naught, and this would be N naught. And if you're wondering what the relationship would be if they were on the same curve, N would be bigger than A would be bigger than C. So like that would be N, that would be activity depending on the half-life, and that would be count rate depending on how you've positioned your Geiger-Muller tube, I suppose. Where that would be N, that would be A, that would be C. How often do I stream? I typically stream twice a week, once for a paper live solve to demonstrate exam technique, and once in a more seminar style like this. Now, as everyone's bringing up, yes, count rate is a thing, background count rate. So we know that radiation does not only come from these radioactive sources being pointed in a given direction. Radioactivity exists all around us for a whole host of reasons. We have some solar radiation coming in through the atmosphere from space. We've got radon gas, which is like radioactive from like rocks. That kind of depends on the sort of geography. We've got medical, we've got some nuclear. We have carbon-14 in us, and carbon-14 is radioactive. There's like potassium in bananas. So actually, one of the things you do in radioactivity is you compare the dose you get to how many bananas you would have to eat to get the same dose of radiation. Yes, so there's this constant background rate. There's this radiation kind of all around us. And so if you just held up, even if there was right here, I assure you, I promise you, FBI, I have no nuclear radioactive materials in this office. But if I held up a Geiger-Müller tube, it would still start firing because there is this constant background rate, which depends on your geography and what your sort of local sources of radiation are. So what does that mean? It means that if I were to hold a Geiger counter, well, in fact, let's. So, given that there is radiation all around us, just from the sort of natural environment, if I did, which I don't, FBI, but if I did have a radioactive source, which I don't, then if I were to hold a Geiger-Müller counter at that, it would count the sort of activity coming from that source, but also some of those counts would be from the natural background rate. So all the background rate that it would have, like if I just held my Geiger-Müller tube like that, I would pick up some count rate. And if I held the source there, all the same background rate would still exist with the new count rate from the radioactive source on top. And so what you have to be really careful of now, if I go back and sort of draw a sample diagram, so I see this is a really common map. So let's say I had a graph that looked like, straight lines are going to be a struggle for me, but like whatever. So let's say I've got my count rate, and let's say I start here and it decays away over time to a nice flat level here. And let's say that's 20 and it starts at 120. So over time, we can see that it has decayed away to a constant level. And that constant level is the background rate. Now, let's be honest. Let's have a look up. It wouldn't actually be constant because of the random nature. It's probabilistic, so it really would be a little bit like noisier. So there would be some like random natural variation in it just because of probabilities. But in any sort of real situation, they're probably going to give you the nice smooth curve instead. And the classic question might be, okay, well, what is the half-life of this? So in fact, this graph is nearly quite well suited for doing this. But the so let's say this was like time 0. Or in fact, hold on a minute. Let me think this through. I mean, I don't think I did it precisely. Well, I didn't do it precisely. But let's say yeah, do you know what? Okay, so what I'm going to do is to say, let's say that this value of 60 happens at like, I don't know, 20 seconds. Is that the half-life? The answer is no, it is not. So if we're talking about a half-life, the half-life is the time it takes for half of the nuclei present to decay. So it will also be the time it takes for the activity to drop to half of its initial value. It will also be the time it takes for the count rate to drop to half of its initial value. Now, you might think that means, all right, this 120 needs to be halved to 60, but that is not true because that 120 is not all from the source. The source only has a count rate of 100. So after one half-life, I would expect that count rate to go down to 50. And I would expect that 50 from the source to be added on to that constant background of 20. So the true half-life would be here when the count rate is 70, not 60. So you kind of need to translate into the true background. So that in terms of the true count, the C naught would be 100. So after a half-life, it would be exactly, you're adding on this constant background rate. So the true count rate would be 100, which means after one half-life, where half-life is denoted by T half. So after one half-life, I would expect the count rate to be 50. And so, or rather what they call the corrected count rate to be 50, corrected for the background rate. And then the actual rate would be that 50 plus the 20 again to get me to 70. So that is how you think about it. translate into true count and then translate back into, or rather translate into corrected count rate and then translate back again once you know what you're once you know what you're working with. So that's what we got going on there. That's how to deal with background rate when you're doing anything with radiation or radioactive decay, sorry. Then the other thing is to work out the relationship between the decay constant and the half-life. So we know that n equals n naught e to the minus lambda t, where we defined the boundary condition that when t is the half-life, n is equal to a half of n naught. And we can plug that boundary condition into the equation to get that relationship between lambda and half-life. So a half of n naught equals n naught e to the minus lambda t, where we can cancel the n naught on both sides and find that, well, there's different ways of doing this. You could just take lunds from this point. I don't like doing that because I prefer to think of this as 1 over e to the lambda t. So I like 2 equals e to the lambda t because that keeps things positive, which I enjoy, which means that ln 2 is equal to lambda t. And so t is equal to ln 2 all over lambda. Now, hold on. So this would be, what I should have done really is say that shouldn't be a general t. This should very specifically be the half-life all the way through. So that is the half-life as a function of this decay constant. If you don't like that method, the other one is available to you, where you take instead a half equals e to the minus lambda t half. If we take ln of both sides, we would get ln of a half equals minus lambda times the half-life. But then that is ln of 2 to the minus 1. And then using your log laws, you would take that minus 1 out the front and then cancel it with the minus sign on the other side of the equation. So again, get the half-life is equal to ln 2 over lambda. So that is an important relationship to hold on to. That relationship between the half-life and the lambda, where again, that lambda is the decay constant, which is the probability of a given nucleus decaying in any given second. So one thing that I have seen asked that people kind of stumble on is they do a bunch of work because the question prompts them in n, and then they're asked to calculate the activity, and they don't conceptually understand that there's just that simple relationship where activity is n times that decay constant. So that's one to really, really hold on to. I'm trying to think. Okay, now someone asked for the specific example of carbon-14 dating or carbon dating. And we can also then talk about uranium dating for rocks. So in terms of carbon dating, the idea is, well, let's have a bit of an off-the-board conversation. We have a lot of carbon in us. We are constantly replenishing the carbon in us by eating. So we have the carbon in us because we are living organic things. When we die, we no longer release carbon, we no longer take carbon in. So what the carbon inside us at the time of our death is locked in at that point. And a small proportion of that carbon is carbon-14, which is radioactive. It undergoes radioactive decay with a known half-life. So while we are living, we are constantly replenishing our carbon, which also means we are constantly replenishing our carbon-14 stores. And because we know the half-life, we know the decay constant, which means we know that is what probability of those carbon-14 atoms are going to decay in us in any given second. And because that probability is fixed, and because the number of carbon-14 atoms in us is fixed, we are emitting a constant rate of radiation from the carbon-14 in us. But the second we die, the second we stop replenishing that carbon-14, that carbon is locked in. As soon as it decays, it is now not replaced, and the activity starts to die away. It starts to follow that exponential decay curve. And so by taking a scan, by sort of measuring the radioactivity coming from a once living source and comparing that with the activity that we would expect when the living source was alive, we can do a half-life calculation. Or rather, we can do sort of calculation where, so let's say this is, where again, the activity A equals A naught e to the minus lambda t, where A naught would be known and A would be measured. Yeah, we can find its age from this, and I'm about to show you how. So this is measured. This is known. And we can rearrange this equation from T. This is also known from the half-life. That's not, I can't, well, hold on, let me just, so that's known. So what we do is to say that A over A naught equals e to the minus lambda t. We can take ln of A over A naught equals minus lambda t. So that's ln A minus ln of A naught equals that. And so t equals ln of A naught minus ln of A, which I get by multiplying that side by -1 all over lambda. So A naught is known, A is measured, lambda is known. So by measuring the activity of a once living source, we can work out how long has passed since the thing died. And this typically works on the order of several hundred to up to, I think it's 10,000 years. It might be, it's on the order of that. It might be more like 50,000 years, but it's on that order of things. And we can do a similar thing with uranium decay, I think it is. So remember, of course, that this carbon dating only happens with once living things, but we can date rocks. So for instance, how do we know that the Earth is like 4 billion years old or however old it is? We do that from the rocks. And the idea is that rocks have, okay, so the way that the rocks work, this is actually quite interesting. So we know that the rocks, I can't remember what the exact isotope is because I don't know anything. I understand things, but I don't know anything. Argon dating is not what I want. Boo. Oh, is it not going to tell me? Oh, that's rude. Oh, wait, no, I have to get into nuclear radius. We'll end with there. Okay, so is there any time you could quickly go over fission and fusion at the end? Maybe, but I'd rather go over nuclear radius if I can. I may have time. Let's see if I can zip. But the main thing I wanted to say, uranium dating, yes. So let's say I've got, so the way that this works, I can't remember specifically what the isotope is, but I'll just say it's 238. Let's say blah, 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 blah. It decays into lead. So what we know is that it started with, there's the amount of uranium that there was, and there was no lead. So initial ratios. So we can kind of compare how much we expect to have of uranium and lead at any given time. So uranium, lead. Initially, we would have all of it being uranium and none of it being lead. And then later, at some time that you measure it, you actually measure the proper ratio. It would be I'll call this a 1-to-0 ratio. And later, you can measure the ratio of uranium to lead. So for instance, if this is now a 1-to-1 ratio, then it means that half of the nuclei have decayed into lead And so that would mean you are 1 half-life old. Similarly, if I had this ratio, so from this ratio of uranium to lead, let's say instead this was a, I don't know, a 1-to-3 ratio, that would mean that a quarter of the remaining nuclei are uranium, so that would be 2 half-lives. And so you get this sense that by measuring the ratio between uranium and lead, you understand how many half-lives have elapsed by understanding that the number of lead nuclei must be equal to the number of uranium nuclei that have decayed. So by measuring the number of lead nuclei, you know how many uranium nuclei decayed, and you know how many are remaining, so you know what sort of N naught would be. So the measured amount of uranium would be N, and the total of the uranium, so N equals the number of uranium, and N naught is equal to the number of uranium plus the number of lead. And then we can plug those two, the N and the N naught, into the half-life equation and work out how old the rock is. So some people get a little bit confused on those applications. Now, I quickly do want to get onto, and I did this in a different stream actually when someone mentioned it, but I do want to quickly get into nuclear density stuff and nuclear radii. So I mentioned this in the turning points video, I remember, because you use electrons and you accelerate them using high voltage to create high energy electrons with a very small de Broglie wavelength, which would be scattered by diffracting through a nucleus. So the wavelength of the electrons is on the order of 10 to the minus 15 meters, which is the diameter of a nucleus. And you get a diffraction pattern, which gives you the diameter of that particular nucleus. So experimentally, we can measure the radius of a nucleus. We do assume a radius is a sphere. We'll kind of get there. So what we find experimentally when we do this over a number of nuclei is that, and if we plot a log graph, if we plot ln R versus ln A, where A is the mass number, we find it has this sort of relationship where it is linear and has a y-intercept ln of R naught. So we can measure this experimentally. We get a sense, we plot this graph and we get a sense of the gradient and the intercept. And what we find is that the gradient is a third. So this is totally empirical. And we find from the intercept that R naught is equal to 1.05 femtometers. So the empirical results, so I don't think we even need to assume things here. Uranium-238 and lead-206. Thank you for that information. So from the empirical results, we find that R equals R naught A to the third. Now, what we can do, therefore, is to say that R cubed equals R naught cubed times A. And then by assuming a spherical nucleus, we know the volume of a nucleus would be 4/3 pi R cubed. So the volume of a nucleus is 4/3 pi R cubed, which would be 4/3 pi R naught cubed A. And then you recognize, well, first of all, that the density is equal to the mass over the volume, where the mass of a nucleus would be the atomic mass number times U. So if it's, for instance, uranium-238, the mass of that is 238U. And the volume is 4/3 pi r naught cubed A, where the A's cancel, and we immediately see that the density of a nucleus is independent of the mass number. Was this theory developed before the standard model? That is knowledge I do not possess. Yes, it was you who asked this. Thank you very much. So yes, from this, we can plug in the numbers for U and R naught to work out that constant density of a nucleus, which is very worth bringing up here. And then in the final 5 minutes, what was someone asking for? A bit of fission and fusion. I'll give a brief overview. Although I could, as we know, we've got about a month before the first major exam starts, so I can probably go back and revise that in like a general session if we need to. But in terms of fission, well, let's start with fusion. Fusion is when two lighter nuclei smash together and form a larger nucleus. This is done typically in stars, where hydrogen is fused to form helium. The conditions required are very high temperatures and very high pressures. Common question. Someone asked where the value of what comes from. It's empirically derived from the intercept of this graph. So understanding your practical physics, a lot of it is converting the model into a straight line and then interpreting the gradient and the intercept. So the gradient tells us this power of 1/3, and the intercept tells us this value of R naught. So just purely empirically from the intercept. Now, back to fusion. So fusion conditions are high temperature, high pressure. The high temperature is required to give the nuclei sufficient kinetic energy to overcome the electrostatic repulsion to get close enough that the strong nuclear force can act. And the high pressure is to make sure they are all close enough that the collisions happen frequently enough that you get these fusion events happening with sufficient frequency. And you can calculate from binding energy, from the mass of the nuclei before and after, how much energy is released from a fusion event. Fission is when larger nuclei split up into smaller nuclei. Typically, this is induced fission, where we have uranium-238. We bombard it with a nucleus, causing it to form the unstable uranium-236, which immediately disintegrates through fission to form daughter nuclei plus 2 or 3 extra other neutrons. The way a fission reactor works is you need to have a controlled chain reaction. So the first thing you need to do is to have those neutrons that go flying off to be able to be absorbed by a further nucleus. When they get fired off, they're actually slightly too fast. They would just sort of ping off the nucleus rather than be close enough to get absorbed by the nucleus to cause a fission event. So we have to slow them down with the moderator, and that's the function of the moderator, to slow down the neutrons to be able to be absorbed by future nuclei. And the job of the boron control rods is to be raised or lowered in order to control the number of neutrons that get absorbed in future fission events. So if you want to increase the rate of reaction, you raise up the control rods so more of the neutrons get absorbed and cause events. And if you want to slow down the reaction, you push in the control rods so more neutrons get absorbed and fewer of them cause future fission events. Induced is instantaneous, yes. The second you get hit by what's functionally instantaneous. So if you get fired with a neutron and that neutron gets absorbed, at that point you disintegrate. And so those are the basics of fission and fusion in terms of a core idea. If you were having a test on this tomorrow, those are the things I would want you to know. I'm going to have a quick scan, but I'm looking at the clock and thinking I probably do have to leave now, but let me have a quick scan and see if there's anything else No, I think the rest of this is details, right? Learning about the specifics of radioactive waste and what we do with it, learning about the properties of alpha, beta, gamma, their different applications. But in terms of the core theory, I think these are the really core essentials that you hold on to. And this is what everything else is kind of built on. So if you understand the things I've gone through today, the specifics of the knowledge points should begin to make sense and fit together. So with that, it is 7 o'clock and I must run. But thank you very much, firstly, for suggesting nuclear. That this is a good shout. And second of all, thanks for continuing to ask loads of good questions in the chat, because it means that I can kind of direct this in a way that's most helpful most helpful to you in the way that I would with, say, like a proper tutoring session. So with that, I'll see you next time for what I promise will be an A-level math run again, where you can watch my skills in action, including my checking technique. And I'll see you again next week for another physics seminar stream. You are very, very welcome. And we'll keep on getting suggestions about what topics you guys want me to cover. Keep dropping them in the sort of Discord server, what sort of stuff you think you need the most help with. But right, I'm going to leave you there, and I'll see you guys next time. All right, take care. Bye-bye.